Good evening, everyone. Welcome to ninth week of NPTEL problem solving sessions for basic electrical circuits course. And in today's week, we will solve a few problems of current year's week 8 assignments, that is on op-amp and negative feedback. And after that, we will practice a few questions of week 9 assignments, that is on first order circuits. So let's begin with it. So first of all, we start with the current year's week 8 assignment. So the first question so we'll start from the we'll go through the questions that were uncovered in the last problem solving session. So the first question that we have over here is we have a circuit for two op amps in negative feedback, and we are asked to calculate the current I naught. We're asked to calculate the current I naught for a given input voltage Vi equal to 10 volts. So in order to solve it, let's assume the voltage at the negative terminal of so let's call this op amp 1 and op amp, let's call it op amp A and op amp B. So the voltage at negative and positive terminal of op amp B, let's call it VB, and the voltages at negative terminals or negative and positive terminals of op amp A, let's call them VA. So now we need to solve this network. So this node is at voltage VB, and this node is at voltage VA. So the current that is flowing through this 10 kilo ohm resistor is VA minus VB by 10 kilo ohm. And since no current can flow in this direction, so all the current that is flowing through this 10 kilo ohm resistor will be the current that is flowing through this 10 kilo ohm resistor as well. So now if this current flows through this 10 kilo ohm resistor, the voltage developed across this will be VA minus VB by 10 kilo ohm, that is the current, into 10 kilo ohms, that is the resistance of this element. So for this node, what we can say is the voltage will be the voltage of this node, that is VA, plus the voltage developed across this 10 kilo ohm resistor. So the total voltage will be 2 VA minus VB. Now, since the input voltage is 10 volts, so this node will be 2 VA minus VB plus 10 volts. And as we discussed in the starting, that we are assuming the voltages at the positive and negative terminal of op amp A as VA. So this voltage is VA. Now the current that flows through this 10 kilo ohm resistor is so from our previous argument, it is VA minus VB by 10 kilo ohm. And since we have found the voltages at both the terminal of this 10 kilo ohm resistor, so from there also we can find the current through this 10 kilo ohm resistor. So VA minus VB by 10 kilo ohm is equal to the voltage developed across this resistor divided by the value of this resistor, that is VA minus uh, voltage of this node, that is over here 2 VA minus VB plus 10. And if you equate that, you get the value of VB minus VA as 5. Now let's proceed. So please keep this equation in mind. And after this, if we go to the, if we further see the path of the current that we found, so again I is equal to 0 for the negative terminal of the op amp. So all the current will flow in this direction. And again the voltage developed across this 10 kilo ohm resistor is VA minus VB, and hence the voltage at the output of the op amp, that is this node, is VA plus the voltage developed across this resistor. So that comes out to be 2 VA minus VB. Now the current, this voltage is VB as discussed earlier, and this voltage we calculated as 2 VA minus VB. So the current through this 5 kilo ohm resistor is 2 VA minus VB divided by 5 kilo ohms. Okay, and since no current can flow in the negative terminal of the op amp, so all the current will be flowing through this resistor R. So I naught can be written as I naught can be written as 2 VA minus 2 VB divided by 5 kilo ohms. And since VB minus VB minus VA we have taken out as 5, so VA minus VB will be minus 5. So the current comes out to be 2 milliamps. Now, one thing that you should notice in this question is that irrespective of this resistance R, this complete circuit is giving you a fixed current of value I naught. And its value depends on what? Its value depends on your input voltage, that is VI. So, what you can say is that this is an ideal voltage to current source. Voltage controlled current source. So, whatever voltage you give, that voltage is converted into output current I naught, and that won't depend on this resistance R. So, and this is one of the realization of an ideal voltage controlled current source. So, let's move to the next question. Now, in this question, you need to find the minimum value of R1. So, you have a circuit in which you have path from output to both the positive as well as negative terminal of the op amps. So, yeah. So, in this question, what you have is you have the output of both. So, from output, you have a path to both negative as well as positive terminal of the op amps. So, in this case, what will happen is you need what you need to see is that uh, what you need to find is the minimum value of R1 so that this complete circuit remains in remains in negative feedback. So what you need to do for this is you have to de-energize the active source, that is this V in. So there will be a ground at the 1 kilo ohm node, and from there so you can break the loop at the output, and from there you can find from VT the gain till both the positive as well as negative terminal. So for the P plus by VT, that is the gain from VT to the positive terminal is so you have 1 kilo ohm and 100 kilo ohm resistors in parallel. So it is a 0.99, that is approximately equal to 1 kilo ohm. So you have this as the gain, and similarly from VT to the negative terminal of the op amp, you have R1 divided by 4 plus R1. So what you need to have is for the circuit to be in the negative feedback, the gain from output to the negative terminal should be greater than what you have from output to the positive terminal. So plugging the values of the gain that we calculated previously in the inequality mentioned over here, what we get is R1 should be greater than 1.33 kilo ohms. So, and this is how you needed to solve this question. Now, let's move to this the last question of current year's week 8 assignment. So here you need to find out in what feedback configuration the circuit is. Now again you have to de-energize both the current and voltage sources. So the current source will become an open circuit, and the voltage source will become a short circuit. So from there, what you have is so this is the network skeleton that you get after de-energizing the voltage and current sources, and from there both from VT to the positive terminal. Now, so since this positive terminal is connected to ground, so whatever this VT varies, this voltage won't vary. So V plus to VT is 0, and again V minus by VT is 0.5 due to the resistor divided between these 5 kilo ohm and 5 kilo ohm resistance. So since V plus by Vt is 0 and V minus by Vt is some positive value, so the gain to the negative terminal is higher. So this circuit is in negative feedback configuration. So these were the questions from current year's week 8 assignment. And now we will move to practice problems for week 9 assignments, that is based on first order circuits. So let's move to the first question. So now in this question, you are given a differential equation corresponding to RC as well. So you have two networks. One is an RL network and another is a RC network. And you have been given the differential equation corresponding to both of the networks. So for RC, it's dV naught plus 500 V naught is equal to dVs by dt. And for RL network, it's dV naught plus 2 into 10 to the power 6 V naught is equal to 2 into 10 to the power 6 Vs. So from these given differential equations, you need to find out the time constants for both RC as well as RL networks. Now, let's move to the RC network first. So, uh, so assume the voltage developed across this capacitor as Vc, and in the question itself, it's given the voltage developed across the resistor is V naught. So from there, what you have is Vs, the voltage source, is equal to Vc plus V naught. Now, if you differentiate this complete equation on both RHS as well as LHS, what you get is dVs by dt is equal to dVc by dt plus dV naught by dt. And now we, from the current to voltage relation of capacitor, we know that the current through the capacitor is equal to capacitance times derivative of the voltage across that capacitor. Now, the voltage developed across the capacitor in this case is Vc, and the currents in capacitor and resistor are in series, so the same current flows through them. So the current through the capacitor, that is I, is equal to C dVc by dt. And so from here, I by C that you get as dVc by dt. So this this thing you can so I by C you can substitute in the equation above, and from there you get the value as dVs by dt is equal to I by C plus dV naught by dt. And also since the current is in series, so the same current flows through the resistor as well. So I can also be written as V naught by R. Now, if you substitute the value of I as V naught by R, what the final equation that you get is dVs by dt is equal to V naught by RC plus dV naught by dt. Now, this RC is the time constant of this RC circuit. So, from the equation, you have RC as equal to 1 by 500, and that is equal to 2 milliseconds. So now let's move on to the RL network. So for RL network, again you have Vs is equal to VL plus V naught, where VL is the voltage developed across the inductor, and V naught is the voltage developed across the resistor. So from and again from the voltage to current equation of the inductor, what you have is VL is equal to LdI by dt. And also, since the current is flowing in series through both the inductor as well as resistor, so I is equal to V naught by R. So from these two equations, what you have is VL is equal to VL is equal to LdI by dt, and I is equal to V naught by R. What you can write is so you can substitute the value of I is equal to V naught by R in the above equation, and what you get is VL is equal to L by R times dV naught by dt. So this value of VL you can substitute in the first equation, that is Vs is equal to VL plus V naught. So from there, what you get is Vs is equal to L by R times dV naught by dt plus V naught. So if you multiply this complete equation by with R by L, so this is what you get. R by L times Vs is equal to dV naught by dt plus R by L times V naught. So from again in question, the differential equation was given in this form, that is 2 into 10 to the power 6 Vs is equal to dV naught by dt plus 2 into 10 to the power 6 V naught. So from question, now we know that for a RL network, the time constant is L by R, and from question we have L by R is equal to 1 by 2 into 10 to the power 6. Hence, the time constant comes out to be 0.5 microseconds. So this is how you needed to solve these two questions. Now let's move to the next question. So in this question, what you need to do is you need to find out the time constant of the overall circuit. So what you have to do is de-energize the energy sources. Now keep in mind that the time constants are not the property of the inputs or the where from where you are taking the outputs, or even for that matter the initial conditions of the energy storage elements. The time constant is merely the property of the skeleton of the circuit. So you can de-energize this voltage source Vs, and that will become a short circuit. So from there you get this skeleton, that is 2 kilo ohm, 2 kilo ohm are in parallel, that are in series with 1 kilo ohm resistor, and the capacitors, the two capacitors are in series at this point. So from here what you get is now the series capacitances can be so we know the formula for series capacitances, it is C1 C2 upon C1 plus C2, and the resistance, the equivalent resistance that you see in the complete circuit is of 2 kilo ohms. So from there you get the value of time constant as RC, that is 2 seconds. So 2 kilo ohms into 1 millifarad, that comes out to be 2 seconds. Now in this circuit you have a you have a parallel combination of an inductor and a resistor, and you have been given a time varying current source, and the value of this current source the with respect to time has been plotted in the question itself. And what you need to find is voltage across this resistor at time equal to 1 microseconds, 2.5 microseconds, and just so this is the on time axis, this is the 0 second, and just at t equal to 0 plus you need to find the value of the voltage across this resistance. And what you can assume in this question is that the steady state reaches after 4 time constants. So, after the time has passed of 4 tau, you can assume whatever. So, you might have learned that inductors are short circuit in a steady state circuit. Inductors are short circuit and capacitances are open circuit. So, all those approximations you can apply after 4 time constants of any transient that occurs. So let's proceed to see how to solve this question. Now, in this question, so the time constant is again L by R, that comes out to be 0.1 microseconds, and uh, again the voltage across this resistor will be the current across this resistor multiplied by the value of this resistance. And now, also, we need to know that in steady state, all since this inductor will be a short circuit, so all the current will flow through this inductor, and the transient. So, from the graph of the current that is shown, it is obvious that the transient occur at 0 microseconds and 2 microseconds. And in the question, you have been asked the value of the current through the value of the voltage developed across this resistor at t equal to 1 microsecond, 2.5 microsecond, and 0 plus. So as far as 1 microsecond and 2.5 microseconds are concerned, so now 1 microsecond is greater than 1 microsecond is greater than 4 time constant. 4 time constant here comes out to be zero point 0.4 microseconds, and one so from transient to 1 microsecond you have 1 microsecond. From first transient to 1 microsecond you have 1 microsecond, so it's greater than zero point 0.5 microseconds. Similarly, from second transient that occurs at t equal to 2 microseconds, you again have zero point 0.5 microseconds at the point where you need to find the value of the voltage across the resistor. So in these both the cases, you can assume the steady state has reached, and if the steady state has reached, that then the inductor will become short circuit. All the current will flow through the inductor, and since no current is flowing through the resistor, so the voltage developed at across the resistors at both of these time instants will be zero. Now let's see what happens at t equal to 0 plus. Now just before the transient occurs, that is at t equal to 0 minus, this is the circuit. This is what the circuit looks like. So a DC current of 10 microampere is 10 milliamps is flowing into the circuit, and all the current. So since the transient has not occurred till now, all the current will flow through this 10 through the inductor only, and the current across this resistor is 0, and the current through this inductor is 10 milliamp. Now as soon as this 10 milliamp current source is removed, now you know, in order to avoid any impulses in currents or voltages, the current across the inductor and the voltage across the capacitor cannot change instantaneously. And why this happens is, so we know that the current and voltage equations of inductors and capacitors, if we write it, what we get is uh, PL is equal to L DIL by dt, and IC is equal to C dVc by dt. Now if there is a sudden jump in either inductor or the capacitor voltage, there will be their derivative will become impulses, and that will create impulses in the voltage and currents of the circuits. So that's why inductor currents and capacitor voltages don't change instantaneously. So using that logic, so 10 milliamp current that was flowing at t equal to 0 minus will still be flowing through this inductor at t equal to 0 plus. Now earlier this current was being provided by an external current source, and now there is no other path for this current to flow. So this current will flow into this resistor. So IR in this case will be equal to minus IL, and that will be equal to 10 milliamps. So the voltage developed across this resistor is minus 10 milliamps into the value of the resistor, and that was equal to 1 kilo ohms. So the voltage comes out to be minus 10 volts. Now if you try to plot the value of the if you try to plot the value of the current on the if you try to plot the waveform of the voltage developed across the resistor, so this is how it will look. So we will plot it intuitively. So on y-axis we have VR, and on x-axis we have time. So for t less than 0, that is the right hand side of that is the left hand side of the origin, the steady state is reached, so there won't be any current flowing through the resistor, and hence voltage will be 0. Now at t equal to 0, what we found out that the value of the voltage across the resistance was minus 10 volts. So that voltage is developed across this, and that slowly decays and settles to 0 after 0.4 microseconds. That is the 4 times time constant. And after that, it remains 0 till the second transient occurs. Now, when the second transient occurs, since the till this point the current across the inductor would have become zero, and suddenly there is a jump of 5 milliamps of current in the complete circuit. So that zero current will be maintained across the inductor, and all this 5 milliamps will flow into this resistor. So the voltage of this voltage across this resistor will become 5 volts. So earlier it was minus 10 volt. Now there will be a spike of 5 volts, and slowly it will again settle down to zero when all this 5 milliamps will start flowing through this inductor. So now again, using the all the arguments that we have studied, we have discussed till now, what we can do is we can also plot the waveform of current through this inductor. So let's see that also. Now current through this inductor. So again, we will on y-axis we have IL, and on x-axis we have time. So t less than zero, the all the current that this 10 milliamp current source that this current source is providing will be in be flowing in this inductor. That so current through this inductor is 10 milliamp at that point, and after that, slowly within 4 time constants at t equal to zero point 0.4 microseconds, this current will fall to zero, and it will remain till zero till 2 microseconds, and after 2 microseconds it will slowly rise and settle to 5 milliamps. So only difference between the current of the time waveform of the input current and time waveform of the inductor is the is a finite rise and fall time. So that you can see over here, like these two things are the differences between the input current and the inductor current. So any doubt in this?
Understood, pa.
Okay. So let's move to another question. Now in this question, what we need to find is you have you have another circuit where you have two inductors and two resistors, and value of these inductances and resistances are given, and again an input current is flowing into this network whose time waveform has been given in the question, and you need to find the values of inductor current at t equal to minus 5 microseconds and t equal to 10 microseconds. Now this is second order circuit actually, but if you find the individual time constants of these two different RL networks, what you get as time constant is both the time constant comes out to be 0.1 microseconds. So at t equal to minus 5 microseconds, that is way before, and this is the 0 microsecond point. T equal to t equal to minus 5 microsecond will come somewhere over here, and t equal to 10 microsecond will come somewhere over here. So at both of these points, what you have is uh, t equal to minus 5 microseconds is way before any transient has occurred in the current, and t equal to 10 microsecond will be much after the final transient that is at 2 microseconds has occurred. So in both the cases, you will have a steady state circuit. Now, in steady state circuit, anything in parallel to in steady state, since the impedance of an inductor is zero, so anything in parallel to that inductor will be can be ignored. So you can ignore R1 and R2. So in steady state, you have a current source that is pushing current into two inductors in series. And since the inductors are in series and series current is equal, so at t equal to minus 5 microsecond, where input current is 10 milliamps, in that case, both IL1 and IL2 will be equal to 10 milliamps. And again, at t equal to uh, 10 microseconds, both IL1 and IL2 will be equal to the input current that is equal to 5 milliamps. So this was a straightforward extension to the previous problem. Now, one thing that you can keep in mind is these are the transformations that you can refer to if you want to quickly build the steady state circuit. So anything in series with a capacitor will be shorted, and a resistor and capacitor in series can be approximated as a single capacitor. Similarly, because the impedance of a capacitor in steady state is infinite, and since the impedance of an inductor in steady state is zero, so anything in parallel to in an inductor can be removed, and it can only be considered as a single inductor. Now, a resistor and capacitor in series. So in this case, since this is an infinite impedance, R equal to infinite, so this can be considered as a single resistor. And similarly, an inductor and resistor in series. In this case, this can be ignored, as here the impedance is equal to zero. So this can be considered as a resistor. So these you can have as have on in back of your hand to draw the steady state circuits. Now let's move to the next question. Now in this question, what you need to do is you have been given an RC circuit, and that has a voltage of V naught. So initially, at time t equal to zero, the switch is closed, and before t equal to zero, this capacitor is charged to a voltage V naught. And at t equal to zero, after this switch is closed, it's asked that at what time this V naught will become 36. The voltage across this capacitor will become 36.8% of the original value. So what happens when you connect a charged capacitor across a resistor? So initially, when the capacitor is charged to some particular voltage, there is an energy stored in this capacitor, and that energy is in form of electrostatic energy, and that energy you can write as half times C V naught square. Okay. Now, as soon as you connect this charged capacitor across a resistor, what happens is uh, the capacitor starts discharging across this resistor. And where does this energy goes? This energy is dissipated by this resistor in form of heat. So what happens is all the electrostatic charge, that is electrostatic energy that is present on this capacitor, will ultimately go to zero, and this the voltage of this capacitor will go to zero, and all the this electrostatic energy by the time the steady state is reached will be dissipated in form of heat across this resistor. So now, since this is a first order circuit, so in first order circuits, what you have is with what rate it will dissipate, and that will be equal to initial voltage times the first order exponential, that is e to the power minus t by RC, where RC is the time constant. So now in the question, it's asked at what time the value drops to 36.8% of the initial value. So what you have is 0.368 times V naught is equal to V naught times e to the power minus t by RC. Hence, e to the power minus t by RC is equal to 0.368. Now, while solving the first order circuit questions, these two key values you can remember.
that is e to the power minus 1 is equal to 0.368, and 1 minus e to the power minus 1 is equal to 0.632. So if you remember these two key values, you can quickly do the calculations of first order circuits. Now, from this value, you get to know that T by RC is equal to T by RC is equal to 1, so T equal to RC. So within one time constant, and the time constant of the circuit is 1 kilo ohm into 1 millifarad, that is 1 second. So within 1 second, your voltage of the capacitor will drop to 36.8% of the original value. So this is how you needed to solve this question. Now let's move to the next question. So in this question, what you have is there is a parallel combination of three resistors, that is R, 6R, and 6R, and there is a capacitor that is initially charged to 1 volt, and at t equal to 0, this is connected across this parallel capacitance of three resistors, parallel combination of three resistors. And in question, what is asked is after three time constants, what will be the current through the first resistor whose value is R in the circuit. So what you need to see is this can be considered as one single resistor, and as discussed in previous question, for first order discharge, the value of as the capacitor discharges through a first order circuit, the value of capacitance with respect to time is given by initial voltage V naught times e to the power minus t by tau. So this voltage is now, since this after t equal to 0, what circuit you will have is you will have this resistor. You will have both 6R resistor in parallel to that, and the capacitor will also be in parallel to these resistors. So the voltage developed across this resistor VC will be the same as the voltage across any of these resistors. So IR can be written as written with the Ohm's law, that is the voltage across the resistor and the current across relationship between the voltage across the resistor and current across the resistor. So IR is equal to VC by R. Hence, the current equation with respect to time, the current through this resistor R equation with respect to time, you get as V naught by R into e to the power minus t by tau. So this the value of this resistor is given as 1 ohm, and initial voltage was 1 volt. So the current through this resistor comes out to be e to the power minus t by tau. Now at t equal to 3 time constants, the current through this resistor is asked. So IR is equal to e to the power minus 3. And in previous question, you saw that e to the power minus 1 is 0.368. So here it will be 0.368 cubed. So that comes out to be 0.0497. So this is the value of the current through this resistor. Now let's move to the next question. Now in this question, you have four resistors connected, and between so there are two resistors in series, two resistors in series. These two have parallel combination, and a capacitor between these two nodes have been connected, and this complete network is at t equal to 0 is connected to a 2 volts battery. And in the question is asked that it is given that initial voltage across the capacitor is 0, and it is asked that what is the values, value of the what is the energy stored in this capacitor in the steady state in nanojoules. Now in steady state, what you will have is this capacitor will become an open circuit, so this capacitor can be ignored. Now in this case, you can in a straightforward manner, you can find the voltages VA and VB. So what these voltages will be: VA will be resistor divider between this 2 ohm and 4 ohm resistor, and that comes out to be 4 by 3. And similarly, VB will be the resistor divider between 3 ohm and 5 ohm resistor, that will come out as 5 by 4. So uh, the voltage across the capacitor in the steady state, that is VC, will be equal to VA minus VB, and that comes out to be 4 by 3 minus 5 by 4. In decimals, it's 0.0833. And the energy that is stored in the capacitor is half CV square. And the value of capacitance in the question is given as 1 microfarad. So it's half into 10 to the power minus 6 into and the voltage across the capacitor square. So that comes out to be 3.47 into 10 to the power 9, and since 10 to the power minus 9, and since it's asked in nanojoules, so it's equal to 3.47 nanojoules. So this is how you needed to solve this question. Now let's move on to the next question. In this, again, in the given circuit, the switch is closed at t equal to 0, and initial voltage across this capacitor is 200 volts, and you need to find and it is given that the capacitor's equation with respect to time is given in the question, is equal to alpha into e to the power minus beta t, and you need to find the value of alpha and beta. So we discussed earlier that in this case, the voltage across the capacitor discharges in form of this equation, that is V naught, that is the initial voltage, into e to the power minus t by tau. So beta from by comparing the equation that is given in the question, beta comes out to be 1 by tau, and alpha comes out to be initial voltage of the capacitor, that is V naught. So V naught is equal to 200 volt, hence alpha is also equal to 200 volts, and tau for this case will be 2 microfarad into 400 ohms. That comes out to be 800 into 10 to the power minus 6. So beta is 1 by tau, so that comes out to be 1250. And what will be the units? The units of beta will be second inverse. So this you can know by the following way, since any argument of either exponential or logarithmic or any function is a dimensionless quantity, time is in seconds, so beta will be in 1 by seconds. So this is how you needed to solve this question. Now let's move on to next question. So in this, what you are given is that initial, so you have been given this network, and in this network it's given that initial current through the inductor is 10 amperes, and what you need to find is the time constant of the circuit. So we discussed this before also, that the time constant of the circuit is the is inherent property of the skeleton of the circuit itself. It doesn't depends on any independent current sources or voltage sources, and it doesn't depends on initial condition. So this initial condition information that is given in this question is redundant. Now I mentioned that it doesn't depend on independent sources, but this voltage controlled, this current controlled current source is a dependent source, and this is the property of the circuit itself. So this you need to take in account while calculating the time constant. Otherwise, what mistake you would have made is you would have removed this this current source as well, and in that case your time constant would have been L by R, and R would have been 30 ohms. So that would have been that would have given you a wrong answer. So please keep in mind that dependent current sources are part of circuit, and that cannot be removed while time constant calculations. So let's proceed to solve this question. Now, first of all, consider the voltage. So let's consider the voltage developed across this 20 ohm resistor as VA, and the current and let's consider the KCL at node X. So at node X, 0.25 times I1 current is flowing into the node, and VA by 20 is flowing through this resistor of 20 ohms that is flowing outside this node, and current through inductor is considered as I1. So that current is flowing out of, again flowing out of the node. So 0.25 times I1 is equal to VA by 20 plus I1. So this is the current. This is the equation of KCL you get at node X, and on rearranging it, you get VA plus 15 I1 is equal to 0, and consider this as equation number 1. Now, equation number 2 we will consider as KVL in loop L1. So what you have is VA, that is the voltage developed across 20 ohm resistor, is equal to the voltage developed across this 10 ohm resistor and this 5 Henry inductor. And what is the developed voltage across this 10 ohm resistor? That is 10 I1. And the voltage developed across this inductor, again through the inductor's current voltage equation, you have VL is equal to L DIL by dt, and substituting that, you have 5, that is 500 is the given value of the inductance times di1 by dt. So this is the second equation. Now if you substitute the value of VA from second equation into the first equation, the final equation in terms of I1 only you get as 25 times I1 plus 5 di1 by dt is equal to 0. Hence, I1 plus 0.2 times di1 by dt is equal to 0. Okay, so from here you get the value of time constant as 0.2. Now, in general circuit, in general first order circuit, what you need to, what procedure you need to follow to find the value of time constant. So that goes as follows. So first of all, de-energize all the dependent source, all the independent sources. De-energize all the independent sources. Then again keep in mind that you cannot de-energize the dependent current or voltage sources. So those are the part of circuit, and after that whatever circuit you get, find the first order differential equation of one of the currents or voltages in the circuit, whichever you find convenient. So here I found out the first order differential equation for current I1. You could have done that for let's say the voltage VA, and you would have ended up with the same form of differential equation. So from there you get the first order differential equation as the following. So let's say you need to find the differential equation for some quantity A. Now this A can be either voltage or current, it doesn't matter. So you will have A plus K dA by dt is equal to 0, and in that case the value, the K that you get will be your time constant. Any doubt in this?
Clear.
Okay, so yeah, fine. So let's move to the next question. So in this question, what you need to find, you have been given the following. You have been given the following circuit, and in this circuit, you need to. So again, this is a first order circuit, and at t equal to 0, the switch is closed, and this 4-volt voltage source comes becomes the input of this network. And just before t equal to 0, that is the initial condition of this capacitor is given as 0 volts, and you need to find the time, the equation with respect to time for VC, that is the voltage across the capacitor, as well as the current through this 2 ohm resistor. So in the first order circuits, what you can have a procedural way of finding these time equations, domain equations. So what is the procedural way? So any element X, either it can be current or it can be voltage with respect to time in first order circuits, is written as X at infinity, that is the value of X in steady state, plus X at 0, that is at the initial condition of X, minus x at infinity into e to the power minus t by tau, where tau is the time constant of the circuit. So how does this works? So you know that any decay or rise in any quantity in a first order circuit will be with this particular exponential, that is e to the power minus t by tau, and at t equal to 0, what you have is at t equal to 0, this quantity will become 1. So you have x of 0 as equal to x, sorry, you have x t of 0 as equal to x of infinity plus x of 0 minus x of infinity. So that is equal to x of 0. And at t equal to t equal to infinity, this quantity will become 0. So you have x of infinity as the value. So this equation you need to keep in mind for solving any for finding out any time domain current the time domain equation or in a first order circuit. And now the time constant comes out to be so you have for finding the time constant, again de-energize the voltage source. So you have 3 ohm resistor and 2 farad capacitor. So the value of time constant comes out to be 6. Now you can see in all the questions the in the exponential, the time constant has been given as 6. So it's e to the power minus t by tau, and tau is given as 6. So from this, you cannot eliminate any of the values. So another thing that okay, now finding out the current and current IT and voltage VC. So first, let's start with VC. So VC, that has been given in the question itself, that initial condition VC of 0 is equal to 0. And for finding the VC at the steady state, you need to draw the steady state circuit. So in steady state, this resistor will become, so this resistor won't be in picture. So what you have is this 2 ohm that is in series with the 2 farad capacitor won't contribute anything, because this capacitor is of infinite impedance. So no voltage drop across this resistor. So what you have is 4 volt voltage source is connected with this 2 ohm. Then again you have a 2 ohm resistor, and in parallel to this 2 ohm resistor you have a capacitor. Now as far as finding the voltages and currents, you need not to consider this capacitor, because again it has infinite impedance, so no current flows there. So the voltage developed across this capacitor, across this 2 ohm resistor, is 2 volts, and that is again the voltage developed across the capacitors. So VC of infinite you have as 2 volts. So substituting the values of time constant VC of 0 and VC of infinite in this xt equation, you get the value as VC of t is equal to 2 volts minus 2 minus 0 into e to the power minus t by 6, that is equal to 2 into 1 minus e to the power minus t by 6. So this equation, this is this is the equation of the current voltage. Now again, similarly finding the value of the current. So again in steady state, that is at I infinite, you can find from here. So that is the current that is flowing. So that is 4 volt divided by 2 ohm plus 2 ohm, because no current flows through this capacitor. So all the and these 2 ohm resistors are in series for this purpose. So the final value of this current is 1 amp. And the initial value, again for initial value, you need to consider this capacitor as a short circuit. So there you have initial value as, so initial for initial condition, you need to draw the circuit as follows. So you have 2 ohm resistor and then again a 2 ohm resistor. So the current that is flowing through this is, so this becomes 1 ohm in equivalent resistor. So current that is flowing is 4 by 3 ohms, sorry, 4 by 3, and that 4 by 3 gets divided down in these two resistors equally because these are of equal values. So 2 by 3 current flows through this resistor. So what you have finally is I of 0 is equal to 2 by 3 and I of infinite is equal to 1. So the I of t equation you get as 1 minus 1 minus 2 by 3 into e to the power minus t by 6, and that comes out to be 1 minus 1 by 3 into e to the power minus t by 6. So this is what you get. So any doubt in this?
Nope, understood.
Yeah. So okay. So these were the problems from my side. So
Mm,
yeah. So we have come to the end of session. Any other generic doubts
no, this
or
session is
something?
good. Session is good. I understand a lot.
Okay. So then thank you for attending. We can end the call.
Okay, thank you, ma.